Hello everyone. So now let's check this section 7.3. So we have sampling distributions and the central limit theorem for this section. So we're gonna first talk about the mean and standard deviation of a sampling distribution. We're gonna use this example, a four-side die. So we have a four-side die that can have the outcome of 1, 2, 3, 4. So let's look at the population mean of this four-side die's outcome first. So the population mean will be mu equals 1 plus 2 plus 3 plus 4, 4 values and divided by 4, which is 2.5. And the population variance will be we just use the formula we learned before, each value minus the mean squared and divided by the population size, capital N, which is 4 for this case. So 1.25, and then we have a population standard deviation equals 1.118. So these are the population information. Now let's draw some samples. So now let's imagine we want to toast this four-side die 3 times. And the sequence of 3 numbers that is observed is a sample of size 3, drawn with replacement from the population we just described. So there are 64 possible samples, and they are all equally likely. So we have 1, 1, 1, 1, 1, 2, 1, 1, 3, 1, 1, 4, and then we just list all possible outcomes for this four-side die 3 times. And this table lists them and provides the value of the sample mean x bar for each. So for getting 1 and 1 and 1, the sample mean x bar is 1. For 1, 1, 2, so we use 1 plus 1 plus 2 divided by, 1 plus 1 plus 2 divided by 3 equals 4 over 3, which is 1.33. So on and so forth, we calculate for each sample what is the sample mean. And then let's look at the sampling distribution. So let x bar be the mean of a simple random sample of size n, drawn from a population with mean mu and standard deviation sigma squared. The mean of the sampling distribution will be just the original population mean. So mu x bar equals mu. So now let's check. Mu x bar equals 2.5. That is from adding all the x bar values together divided by 64. So we got 2.5. Is that the population mean? Yes. That is the same as the population mean. And the standard deviation of the sampling distribution, we call it sigma x bar. What is the sampling, which is standard deviation of the sampling? So sigma of all the values. So we have 1, 1.33, 1.67, up to 4. All of those sample mean, we look at the standard deviation of those. We can definitely calculate that. Just we have 64 numbers, but we can still use the shortcut formula to calculate the population standard deviation, and that is 0.6455. So based on this theorem, we know that the sampling distribution should be the original sigma divided by square root of n. So let's see whether it equals. The original standard deviation will be 1.118. 1.118 divided by square root of n. So we have a size of 3. So we can calculate this using a calculator. And from this calculator, we got 1.118 divided by square root of 3, 0.6455. So it is exactly as what we got from the table 1. And we also say sigma x bar is something called the standard error of the mean. Standard error of the mean. is actually the standard deviation of the sampling distribution. So these numbers listed in table 7.1, we call those a sampling distribution. And then we have a sampling distribution mean, and we have a standard deviation for that sampling distribution as well. And now we can look at this central limit theorem. As the sample size n increases without limit, the shape of the distribution of the sample means taken with replacement from a population with mean mu and standard deviation sigma squared will approach a normal distribution. So as long as your n is large, then no matter what original distribution it is, you will have a normal distribution for the sampling distribution. So the normal distribution will have a mean mu and the standard deviation of sigma over square root of n. So we know this as well. So note 1, when the original variable is normally distributed, the distribution of the sample means will be normally distributed for any sample size n. Or when the distribution of the original variable is not normal, for any distribution you must have a sample size of 30 or more, then you're gonna get a normal distribution for the samples. And the larger the sample, the better approximation will be. That's the central limit theorem. Now let's look at a problem related with the central limit theorem. A.C. Nelson reported that children between the ages of 2 and 5 watch an average of 25 hours of television per week. Assume the variable is normally distributed and the standard deviation is 3 hours. So we have x follows a normal distribution with 25 as the mean and 3 as the standard deviation. So that is the random variable. If 20 children between the ages 2 and 5 are randomly selected, so we have a sample of 20, so n equals 20 now. N equals 20. Find the probability that the mean of the number of hours. So find the mean, which is x bar. So we want the probability of x bar will be greater than 26.3. So now we want to look at the sampling distribution. So given x, which is the original distribution, what sampling distribution we can get? Since this is a normal distribution, so we don't have a requirement for the sample size to be more than 30. Then we say x bar follows a normal, because the original distribution is normal, with mean, with mu of x bar equals the original mu. So this is mu, and this is sigma squared. And then the variance will be, the standard deviation will be sigma x bar, will be sigma over square root of n. Don't forget the squared, because this location will always put the variance. So that's gonna be sigma, which is 3 over square root of 20 squared. So we know this new distribution, which is the sampling x bar. So this is totally new, because x bar is different than x. You can use y, z, or other letter to represent it. It's nothing related with x anymore. It's just for the mean and standard deviation, we can get some information from the original one. Then now it changed to a normal application problem. We want to know probability of x bar more than that. So 1 minus probability of x bar smaller than 26.3. So smaller than, and then we can transfer, right? 1 minus probability of z smaller than 26.3 minus mu x bar, which is 25. So this is mu x bar over sigma, which is sigma x bar, which equals 3 over square root of 20. So we can calculate this number, which is 1 minus probability of z smaller than 26.3 minus 25 divided by 3 over square root of 20. So that's going to be 1.93, 1.94. So 1.94. Then we check the table, go to 1.9, and then 0, 1, 2, 3, 4. 1.94 is right here because you got 0.04 here. So that's 0.9738. So that equals 1 minus 0.9738. So which tells us it is 1 minus 0.9738, 0.0262. That's the result. So find the probability that the mean of the number of hours they watch television will be greater than 26.3 hours. That probability is only 2.62%. It's very low. Okay, that's all for section 7.3, and then all for this chapter as well. So don't forget the worksheet 7. Worksheet 7 will be posted, and then we will also post the due date for this worksheet 7 as well. Thank you.